is Hanna SHIN, and I'll be talking to you about calculating molarity. Because I'm assuming that most of you have already taken any sort of chemistry or something like AP chemistry, I won't be going over too much about calculating molarity itself, but more on the real-life applications of this topic. So first, molarity. It's expressed with capital M as the SI unit, and it's the number of moles of a solute in a solution. Moles here is a unit of the mass of a substance with 6.023 times 10 to the power of 23 particles of the substance. Simply, we can just think of moles as a number, this number here, which is also called Avogadro's number. So stoichiometry is the entire concept of calculating molarity. It's measuring the reactants and products of a chemical reaction using moles. So 1 mole of a substance is equal to the atomic mass of the substance. So we can see carbon-12 here. 1 mole of carbon is equal to 12.01 grams, as we can see from the atomic mass on the periodic table. And 1 mole of hydrogen is 1.008 grams, and 1 mole of oxygen is 15.999 grams. So because it's easier to just go straight on to the examples for a better understanding, we'll just start with a stoichiometry question. So we have Fe2O3 plus Al as the reactants, and on the right side we have the products, Fe plus Al2O3. So stoichiometry problems usually come in the form of something like, if we have a certain amount of this molecule or an atom, then how much of the other molecule or atom do we need for this reaction to happen? So here we have, if we have 61 grams of Fe2O3, how many grams of Al or aluminum do we need? So the first step of stoichiometry is first to balance the equation. Usually questions will already come balanced, but sometimes we do need to balance the equation. And for a reaction to be balanced, we need to make sure that each atoms on the reactant side and each atom on the product side must be equal. Number of atoms must be equal. So we have 2 Fe molecules, Fe atoms or iron atoms, 3 oxygen atoms, 1 aluminum atom, and on the product side we have 1 iron atom, 2 aluminum atoms, and 3 oxygen atoms. So because this is imbalanced, we're going to need to balance this reaction. First, we can see that we have 1 Fe, 1 iron atom on the product side, but we have 2 iron atoms on the reactant side. So we're going to be using coefficients to balance the equation, adding a 2 in front of the Fe. So now we have 2 iron atoms on both sides. But we also have 2 aluminum atoms on the product side, but only 1 aluminum atom on the reactant side. So we're going to have to add another coefficient in front of the aluminum to balance this equation. So now we have an equal number of atoms on each side. 2 iron atoms, 3 oxygen atoms, and 2 aluminum atoms. So the second step is to calculate the mole ratio. So on the reactant side, since we have to figure out if we have 61 grams of Fe2O3, then how many aluminum atoms, how much of aluminum we would need, we can see that for every Fe2O3 molecule, we need 2 aluminum atoms. So the mole ratio of aluminum and Fe2O3 would be 2 moles of aluminum per 1 mole of Fe2O3. The third step is to convert the mass into moles as the units. We can find the atomic mass of each element on the periodic table. So here we have Fe2O3, 2 iron atoms. So that is roughly 56, rounded to the whole number. we have 2 of those, so we would multiply 56 by 2, plus we have 3 oxygen atoms, so we would multiply 3 by 16, roughly 16, and that would give us 160 atomic mass units. But remember that 1 mole of a substance is always equal to the atomic mass of the substance. So 1 mole of Fe2O3 is 160 grams of Fe2O3. And then we would look at aluminum. Aluminum on the periodic table is roughly 27 atomic mass units, so 1 mole of aluminum would be 27 grams of aluminum. And the 4th step is to calculate the number of moles given. So we can see that 1 mole of Fe2O3 is 160 grams. But the question is asking us, what if we have 61 grams of Fe2O3? So we would divide 61 by 160 and to figure out the number of moles that we have. So that is 0.38 moles of Fe2O3 that we're given. Step 5 is apply the moles to the mole ratio. So recall that the mole ratio for aluminum and Fe2O3 was 2. And 61 grams of Fe2O3 was 0.38 moles. We would need to multiply 0.38 by 2 because of the mole ratio of 2, and that would give us 0.76 moles. And then we would multiply 0.76 moles of aluminum with 27 grams of aluminum, which would give us 20.52 grams of aluminum for this reaction to occur if we had 61 grams of Fe2O3. And here's another question. If we have 30 grams of C6H12O6, this is glucose, how many grams of O2 do we need? So the first step, again, it's to balance the equation. We have 6 carbons, 12 hydrogens, and 8 oxygen atoms. We have 1 carbon, 3 oxygens, and 2 hydrogen atoms, but we need to balance this equation. If we put a coefficient of 6 in front of CO2, that would give us 6 carbons and 12 oxygens, but this isn't balanced yet. We also need to put in a 6 in front of the H2O, so now that would give us 12 hydrogen molecules, as we can see, and another 6 of the oxygen atoms. And here we have to add another coefficient of 6 in front of the O2 to balance the equation. So now we can see that we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms, and the same for the other side. Second step is to calculate the mole ratio. Again, we have for every C6H12O6 molecule, we have 6 O2 molecules. So that would give us a ratio of 6. Number 3, convert the mass into moles. So again, we have the periodic tiles of the elements that we have. Carbon, there are 6 carbons in glucose, so 6 times 12, roughly 12. Plus, we have 12 hydrogen atoms of roughly 1. And we have 6 oxygen atoms of roughly 16. So we would multiply that and add them together, which would give us 180 atomic mass units. But again, remember that 1 mole of a substance is always the atomic mass of the substance. So that would give us 180 grams for 1 mole of C6H12O6. And then we have O2 here. We need to multiply 2 by 16, which will give us 32 atomic units. But again, 1 mole is 32 grams of O2. The third step is to convert mass into moles. So here we have C6H12O6, which what we solved previously was 180 grams. But the question is asking us, what if we have 30 grams of C6H12O6? So we would divide 30 by 180, and this would give us 0.167 moles of C6H12O6 if we had 30 grams of glucose. First step is to calculate the number. First step is to apply the moles to mole ratio. So we can see that we have a mole ratio of 6 moles of O2 for every C6H12O6, and for O2, 1 mole is always 32 grams. So we would, so 30 grams of C6H12O6, as we saw previously, was 0.167. Because of the mole ratio, we would multiply that by 6, and that would give us 1.002 moles of O2. So now we would multiply the number of moles with the number of grams of O2, which would finally give us 32.06 grams of O2 if we had 30 grams of C6H12O6. And now we would be going on to the applications of stoichiometry in everyday life. So stoichiometry is very common in chemistry, and basically any industrialized company would use stoichiometry because they would need to know this to make their products and make sure that their chemical reactions would make their ideal products. So here we can see rockets which need to be calculated using stoichiometry. So we have the RS-225 engine in NASA, and these are basically fuels for the space shuttle, which take people and other things into space so that the International Space Station can use those things. So the RS-25 engine is fueled with liquid hydrogen and liquid oxygen, as we can see, and this would create a byproduct of water and energy for the fuel of the space shuttle. But if stoichiometry wasn't used for calculating the amount of each reactant we need for this reaction to happen, we don't know what's going to happen to the RS-25 engine. It might blow up, or there's something that is undesired might happen. So that's why we need to use stoichiometry to calculate each reactant for this reaction to happen. We can also use stoichiometry for different products. So things like toothpaste. We use stannous fluoride into toothpaste so that we can prevent tooth decay. But again, we need to make sure that the amount of stannous fluoride is clear if you want to know whether the amount of that is perfect for toothpaste. And we also have aspirin, which is used in medicine. We also need to make sure that each reactant creates the desired products. And also, we need to use stoichiometry when we want to make food. So let's say that we have cookies, and you would use stoichiometry to figure out the amount of flour you need to make a chocolate chip cookie. So if the amount of flour is not correct, then your cookie would probably taste very bad. So that's why we would need to use stoichiometry to make sure that all the ingredients are the right amounts for the perfect cookie. So yeah, that was it of calculating molarity. Thank you.
So let's have a time for Q&A session. Now keep going on your lesson. Q&A 안 해?
Q&A. Okay, so does anyone have any questions?
역시나 이럴 줄 알았어. 생각보다 짧지 않았니?
네, 좀 떨려서 빨리 얘기했었던 것 같아요.
그래? 보니까 초반보다 한나가 뒤쪽에서 목소리가 좀 풀리네. 그지? 그래서 그 이야기할 때 조금 더 이렇게 내 목소리 볼륨을 좀 키우면 좋을 것 같고, 한나 같은 경우에는. 그 다음에 저기 슬라이드 쇼 할 때 포인터 지정할 수 있잖아. 그러니까 마우스에 포인터가 지정이 돼 있는 것하고 그냥 있는 거하고 좀 다르거든. 그래서 포인터 지정은 앞으로 다음 강의하는 친구들도 꼭 잊지 말고 지정을 했으면 좋겠고, 그 다음에 무의식 중으로 이거 그 포인터 가지고 막 이렇게 왔다 갔다 하는 친구들이 있을 수 있거든. 그러니까 그거 습관 고쳐야 돼. 그 다음에 그 오른쪽 하단에 지금 한나 같은 경우에도 강의할 때 선생님이 그 한나 모니터 화면을 오른쪽 하단에다가 그냥 배치를 시켰어. 그래서 초반부에 조금 그게 겹치는 그 슬라이드가 있었거든. 그래서 요거는 그때도 얘기했지만 선생님이 동영상 다 저기 업로딩을 해서 너희들한테 보여주면 무슨 얘기인지 알 것 같아. 그러니까 슬라이드 쇼 할 때 오른쪽 하단이나 아니면 오른쪽 상단 같은 경우에는 그 왜 우리가 유튜브 보면 유튜버들 밑에 화면 뜨는 거 알지? 우준이 그런 영상 본 적 있지? 그러니까 그것처럼 해서 화면이 배치가 돼야 되니까 거기에 대해서는 생각을 한번 더 해봐. 전반적으로 그 툴이나 아니면 진행되는 것들은 깔끔했어.